Hi, this is Hong Tao from the AI Assisted team. In this video, I'm going to talk through Embeddings 101, a very brief, very basic introduction to embeddings. I'll start this video by answering these 5 questions. What is an embedding? What can be embedded? And most importantly, how can we obtain an embedding and how to use them? And finally, their limitations. So first, what is an embedding? An embedding is very simply a list of numbers or a vector or a point in some high-dimensional space. It is beneficial to think about embedding as a point in some high-dimensional space because you will see later that this geometrical explanation will help understanding some of the properties of embedding, like similarities and distances. Notice those 3 descriptions are equivalent. So on a high level, an embedding is a compact representation of a thing that you're trying to embed. The important word here is the compact. Now, imagine you are trying to embed a long document or a video, an audio file, some large entities. And by the end of the day, you are getting a list of numbers only of a few hundreds or a few thousand. So in a sense, it is the information has been shrink down into a very, very compact representation. And that's what we want because it is easier to use and easier to store, and they can encode nice properties like distance. Second, what can be embedded? Pretty much anything. A block of text, a block of codes, even graphs, images, videos, audio files, basically anything that has a proper digital representation can be embedded. However, with different entities, they do require slightly different embed techniques because their representation are different. For example, images are represented by pixel values of RGB, and text are represented by characters, which are represented by either ASCII or UTF-8. So because they're different, you need to apply different techniques. So how can we obtain embedding? It is a very complicated topic, and decades of research have gone into it to find a good comprehensive representation of the thing, like how do you embed. However, nowadays with large language models, it becomes easy, almost trivial to obtain an embedding because you can just call a model. But in this video, I like to dig a little deeper into how large language models can compute an embedding for you. We can ask a chain of questions. How can you obtain embedding? The answer is using LLMs. How does LLMs compute embeddings? The answer is using an encoder block based on transformer. What is a transformer? It is a deep neural network with self-attention, 3 matrices, key, query, and value, etc., etc. And why the output embedding can capture the meaning or the semantics of the input? Because the way the model is trained. So how is the model trained? You see, we can ask a chain of questions, almost never ending. And for the purpose of this video, I like to stop here. So I will explain what is an encoder block and very briefly what is a transformer. Let's focus here with it on this graph first. Let's ignore the text for now. So a large language model looks like this, a simplified version. You have your input sentence, hey there, blah, 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 bye. So that's your input text or a conversation, whatever. And then each word are passed into a transformer block. And the output of this transformer block are passed into another transformer block. So you stack multiple transformer blocks on top of each other. And as a whole, they are your model. So basically, the text input, and for each text, for each word, you have a embedding here for that word specifically. And then we insert 2 special words or tokens. One is called SOS. It stands for start of sentence or start of sequence. The other one called EOS, end of sequence. So we insert these 2 tokens, and they also get their own embeddings at the end. And then we choose this one. as the embedding for the whole sequence. So let's try to understand it here. The transform block will output the embeddings for each word, but what we want is the one embedding for the whole sentence, right? How can we obtain that from like each individual embeddings? Well, the simplest thing is we can average them, but by averaging we lose a lot of information, so we don't want to do average. And the one of the clever things with transformer is inside the transformer, each word or token here will adjust its own embeddings based on all the other tokens. So here the end of sequence token will gradually adjust its embeddings layer by layer based on all the other tokens in this sequence. So we can just choose to use this one as the embedding for the whole sequence. And that's a clever thing that transformer allows us to do. So this is basically very briefly how a large language model compute embedding for you. This whole block is called an encoder block. And we in the end, we just use the last embedding, the embedding for end of sequence as the embedding for the whole sequence. Next question is how can we use an embedding? Really, this question depends on how what you intended to do with an embedding, what your downstream task is, what your application is. I can't tell you exactly how you can use them, but there are some nice properties of embedding that I can show you. Hopefully, those properties will help you decide how can you use an embedding. So properties of an embedding. First one, as embeddings should be considered as a whole. Part of an embedding doesn't make sense. So for example, let's say we have an embedding of length 1000. So it's a vector of 1000 numbers. You can't just use the first 500 and compare with another vector of 500. You have to use every single number of the 1000 numbers you have. So those 1000 numbers is one vector. They are one entity. You cannot just slice them. And embeddings are model specific, meaning if you get one embedding from an OpenAI model and another embedding from a Google model, you shouldn't really compare those two in a meaningful way. They are not comparable. Each model are trained on their own objectives and their own data, and as a result, their embeddings are specific to their model. And lastly, the meanings of the embedding. So the embeddings are meant to be a representation of the thing. So the meanings of the embedding are encoded by their distance or cosine similarity. So we will explain more on this with a demo later. So just know that one embedding probably don't make any sense. However, many embeddings and many points in some space together, their relative distance to each other, that's how you encode the meanings. Are there any limitations to embeddings? Yes. So the first one, the most obvious one is they cannot handle long text. Well, this one is specific to the way the large language models calculate embeddings, the transformer blocks I showed you before. You see here the length of the sequence is predefined. If this length is defined to be 1000, you give me a sequence of 2000 words, then it cannot be embedded. So this is a huge limitations. However, there is a way to get around this. There are some summarization models out there. You can summarize a long text into a block of shorter text, which can be fit into your embedding model, and then embed that summarization, provided that summarization works fine. So there are workarounds to this limitation. Second one, because embeddings are just a list of numbers, it's not really human readable. does not offer good explainability, and it's really hard to evaluate the quality of an embedding. And thirdly, the similarity is not well defined. For example, well, we will see an example of this in the demo later. But for example, you are trying to compare two things, and these two things can be similar in different ways. For example, you compare a cup with a keyboard. Well, they are similar maybe because they are both hard, but they're not similar in terms of their shape. So you don't know which aspect of the object is your embedding capture. So is embedding, if embedding captures the softness or the hardness of the material, then a cup and a keyboard are similar. But if they capture the shape, then they are very not similar. So similarity is not well defined. It is defined through the data the model is trained on. So basically, it's a data-driven similarity. So we cannot. It's very hard for us humans to understand what exact similarities did they capture. Okay, now let's jump into a demo and see embeddings in action. So here I'm gonna get some embeddings of a piece of text using both OpenAI's model and Google's model. And the process is very easy. Here I'm just following the official OpenAI's example. Now let's I've already run this, but let's run it again. Clear outputs. Yeah, let's run all the setup code. Okay, so here I have a very, very long text. I had a really good time times 50. So this is the same sentence repeated 50 times to simulate a long block of text. And let's see if it works. Yeah, it works. And the embeddings are, if you want to take a look at the embedding, it looks like this, exactly as we expected, a list of numbers. See, this is not human readable at all, right? We can't tell anything from this. Now I'm going to show you what happens if your text is longer than what is allowed by the OpenAI model. Let's repeat this same sentence 5,000 times and see what happens. We got an error. It says the model's maximum context length is this number of tokens. However, I requested this number of tokens. This tells me the OpenAI model can handle a maximum of this many tokens, and anything beyond that will give you an error. You can trim down your text, or you can, like I said, use a summarization model to summarize your text into smaller block of text and then pass into the embedding model. Next, I'm going to show you a very important property of an embeddings is that they are normalized. Let's first see if they are normalized. So I'm here calculating the norm of the embedding. You see the norm is 1. Norm here just means the length of the embedding. And the length of the embedding is defined to be, remember I said the embedding is a point in some high dimensional space. So the length of that embedding is the distance between that point to the origin, and which is it is also called a norm. So we'll use the norm here. The norm is 1. So this embedding is normalized. And why this is important? Because if you want to calculate the similarities between two embeddings, the distance measure usually we use is cosine similarity. If the embeddings are normalized, like it is now, you can simply do dot product to get cosine similarities. If they are not normalized, you have to normalize them first. Otherwise, dot product will give you a wrong answer. So this is very important. And now so this is OpenAI model. Now let's see the Google model. So we'll see two things. First is how will Google model handle longer text than what is allowed? And then the second one is the Google model embedding from the Google model also normalized? So let's run the setup code. Yeah. Also, a note here is the Google model is private access only. So if you don't have access, you cannot run this code block. Yeah, so we've run all the setup code. Now we do the same thing. So we encode this very long sequence. I had a really good time, times 100 times. Uh, um, ah, let's delete that for now. Okay. Now I see if this embedding is normalized. Again, I'm calling the norm function on the embedding, and we see again it is 1. So the embeddings from Google model is also normalized. Um, these models, Google or OpenAI, because they provide an API, so it is likely that their embeddings are normalized for you. But if you're using some other open source models, it is important to normalize to check if the output is normalized. If not, really you should normalize them first before you do any distance calculation. So now let's see how the Google one handle longer text. So previously we repeat this sentence 100 times. Now let's see, maybe 100,000 times. Is it too long? What about 10,000 times? Yeah, okay. So 10,000 times also works. That does it mean the Google model can handle longer text than the OpenAI model? It's really not. It's really not the case. The Google API will truncate the sequence for you. And I can demonstrate that by embed two sequences. One, I repeat this sentence 10,000 times. The other one, I repeat this sequence only 5,000 times. Okay. Yeah, so now we get embeddings for both sequences, and I can show you that they are the same. So I'm here doing a all close check on the first embedding versus the second embedding. Notice the only difference is that their length is different, and they return true, so they are the same, which tells me that the Google will truncate any sentences or a sequence of text longer than its maximum allowed tokens. So OpenAI will throw a error, and Google will silently truncate the sequence for you. So it's important to know how the API handles your request. So now we've seen the embeddings from both OpenAI and Google, and we know we notice two things. One is each of them have a maximum length allowed. Second is their return embeddings are normalized. And now we move on to a more interesting demo. This one I call a poor man's recommendation system, because embeddings can capture similarities. So one of the naive application is that you can recommend similar items based on some history or based on the existing items, like books, movies, musics. So here, in this example, I'm recommending books. Let's suppose that I shop on Amazon and I already bought these 3 books. One called CMAS. It's actually this one. I'll show you. CMAS, building muscles from calisthenics movements. The other one called deep learning. And third one called the Kubernetes book. So let's suppose I already read these 3 books and Amazon is trying to recommend me a new book to read. So what embeddings allows us to do is we can first embed the 3 books. Here the text is just the abstract. So here I'm using this block of text as the content or as the abstraction of the whole book. So let's encode the 3 books I've already read. And for this example, we're using the Google model. And now here we're just calling get embeddings for the 3 block of text, and then put the results in a variable called inventory. This represents the book I've already bought. Yeah. Before we move on, let's see the similarities between these 3 books. By the way, I'm using a function called getSimilarity, which is defined here. And you see, before I calculate the cosine similarities using the dot product, I do normalization first. It's helpful. It's safer to do it this way because you never know whether the embeddings you get from your models are normalized or not. So it's always safer to normalize again. Now we have the 3 distances. Yeah, let's look at them one by one. So the C stands for the CMAS, building muscle, and D is deep learning. Let's see how close they are. 0.65 distance. Sorry, similarity. So not very similar. What about this one? The deep learning book to Kubernetes book. Both are kind of in the same in the area of computer science. So you should expect this one to be higher than this. And let's see if that's the case. Oh no, there's an error. Sorry. You see, I'm calculating the embeddings, the distance of the deep learning to itself. Of course, this will be 1. But what we want is deep learning to Kubernetes, right? Kubernetes. Yep. Yeah. So the distance, or sorry, the similarity between the deep learning book and the Kubernetes book is 0.8 almost. So it's higher than this, as expected. Okay. So now let's suppose Amazon wants to decide which one to recommend me to read more. Whether it wants me recommend me a cookbook or a reinforcement learning book. Well, as expected, the reinforcement learning book, it is likely to recommend me the reinforcement learning book because I've already read the deep learning book. But let's see if the embeddings agree to our intuition. I'll show these 2 books on Amazon. Here is the reinforcement learning book. And again, I'm using this block of text as the representation of the whole book. And then here is the cookbook. I just chose one that is really popular. Let's see which one recommends, this system will recommend me. And as usual, we will get the embeddings for these 2 books respectively. And now let's see the distance between this the cookbook to all the to my inventory, to all the 3 books that I've already read. You see they are very similar, around 0.7, 0.69. So the distance between the cookbook versus to my 3 existing books, um, they don't differentiate it from each other. So they are very similar. There's no closer or more similar, less similar, just 0.7. What about the reinforcement learning book? You see here, we have a clear window. The reinforcement learning is very similar to deep learning. The second one is less similar than the Kubernetes book, and is least similar to the building muscle book, which this works as we expect. So this, of course, this is not perfect because several reasons because why this is not perfect. One is I'm using this marketing material, like the marketing material for the book as the book itself. So this is not a good summarization of the book. So this will introduce a lot of noise. Second is the embedding itself. We don't know what the embeddings is capturing because the text are all like marketing materials. So maybe their styles are similar because they are trying to sell you the book. Their styles are similar, and the embeddings, we don't know if the model will capture their writing style or the actual content. So in the case of the cookbook, in the case of cookbook, you see, although they are all at 0.7, so kind of similar. But really, if you think about it, the cookbook is not similar at all to deep learning, to Kubernetes, or even to building muscle. So why 0.7 is not a low number? Probably because the writing styles of these marketing materials. So this just shows you that you need to properly think about what similarities means in your downstream task before applying these embedding techniques. Yeah, and that's it all for this video.